Today I will talk about some work I did with my supervisor, Professor Mr. and our chief who's sitting back there during last semester. It's on the secure communication in wireless broadcast networks. So, okay, the motivation. So, what do we mean by secure communication in a network? Usually there are four aspects that's being considered as the security of communication. The first thing is secrecy. We want to keep the confidential information hidden from the adversaries. And the second aspect is the authentication. When I receive some information, I need to know that's exactly who, it's exactly from the source. And the third aspect is integrity, which means that I want to receive the information as it is sent by the source. And the fourth aspect is the non-repudiation. Once the source and the destination found an agreement, the source cannot drop that agreement, and they has to either stick to that agreement, or they will form a new agreement. So, but there is no turning back. So in this work, we focus mostly on the integrity of the information, and in particular, we focus on the detection of any attack or corruption of the data being transmitted. So, why do we care about integrity, and why we care about detection in particular? Because the first reason for me is that it's the weakest requirement for communication to make any sense. Because if you cannot be sure that you get the data as it is, what's the point to communicate? You can just get some random junk. So, and of course, with the detection, it enables us to design a robust system to tolerate failures in the system or attacks from the outsiders. Okay, so if we consider the capacity of detection in a network, or we first look at what do we know in the classical coding theory. So there is this singleton bound that's C minus T as the capacity of detection with a block coding. The block length is C, and T is the maximum number of bits that can be attacked, but that can be corrupted. So this singleton bound is expanded to the communication in networks, especially in the network coding communities. So in 2006, Liang and Kai has proved that the capacity of a network under an attack of adversary is C minus T, where C is the mean cut from the source to the destination, and T is the number of unique capacity links that can be attacked by the adversary. And they also show that this capacity of detection can be achieved with linear network codes. And a year later, from Jackie and his co-workers, they found that this capacity of with network coding can actually be achieved with random linear network codes with high probability. So that's good, because random linear codes is very simple to implement distributively. But however, both of these works consider a very conservative model of the adversaries. So they assume that the adversary can attack at any T unique capacity links in the network. But in reality, most of the time, in the ad hoc network or distributed system, usually it's a node being attacked by the adversary, and the adversary can control all the outgoing links of that compromised node. So it's more practical and very interesting to look at the capacity with no adversaries. So let's look at this example topology with 4 nodes, S trying to send some data to D, and there are two nodes in the middle that can relay the data. And these links here are broadcast links. S broadcasts data to A and W, and A can broadcast its data to W and D. So what's the capacity of this network if we want to detect an attack either by the A or W. So what's the capacity for detection? So if we use that singleton bound with C being the mean cut of this network, which is R, the broadcast capacity of the source, and T is also R, since the adversary can attack either A or W. When it attacks A, it can corrupt at most R bits of the data. So does that mean the secure capacity of this network is 0 because C equals 2 to T? The answer is no. The capacity is R. The way to achieve this capacity R is very simple. Let's just do a broadcasting. Suppose R is 3, so it sends ABC, and then A broadcasts that. Suppose the adversary attacks at A, so it corrupts a part of the data, and then, however, because of the broadcast nature of these two channels, W can get both the transmissions from S and A, and W is a good node, and he can compare these two packets and see a mismatch. So W can raise an alarm to the destination by sending just one bit of the as the notification. So so we know this is it's easy to show that you can never achieve more than R in this topology. So we know the capacity of this network is R. And however, in general, for general network topologies, larger networks, we know nothing about the secure capacities when the adversary can attack on nodes rather than links. So to approach the solution of finding the capacity of under the node adversary, we started thinking. So let's introduce our models for our work. So for network model, we assumed we are given a topology that's a cyclic graph with the set of nodes V and the set of edges E. And of course, each link in this network is associated with a link capacity function C, which maps from a link to any real number. And then for transmission model, during this talk we will only consider the pure broadcast transmission model. So in which all the children of the transmitter receive the same packet and receive all the packets that's being transmitted by the parents. And so actually, and given this model, we have that each outgoing link from a single node has the same capacity, and we also enforce a constraint on the node broadcasting capacity, which is that the total number of information, the total amount of information being broadcasted by a node must be at most CV, V being the node broadcasting the information. And for the adversary model, we assume an omniscient adversary which knows everything in the network, including what's being done at other nodes and what will be done at other nodes. There is no secret being hidden from the adversary. This is a very strong adversary model.
Is CE relevant to the model?
Actually, no. This model works. We don't need a pure broadcast model. It can be pure unicast, all the links uncorrelated, or it can be a mixed model. But in this talk, we'll just talk about the broadcasting. You only need to modify one constraint, and then all the results should hold. So, okay, in this talk, we'll just focus on a very simple linear code, and try to see what we can do. What's the best we can get from that? So we call this code, this algorithm, duplicate and forwards. So in this code, only the source is performing coding, and only the detection is performing. Only the destination is doing detection. None of the intermediate nodes will compare packets and raise an alarm as in the previous examples. And so all the intermediate nodes in the network just forward the packets they receive. And we call a packet being duplicated by a node U if it is sent by U and is forwarded by at least two children of U. And the reason we consider the case when only the source performs coding is that since the source is doing the broadcasting, all its neighbors receive all the packets being transmitted by the source, and the neighbors of the source can jointly code the packets as if it's already coded at the source and being unicast to the neighbors of it. So for example, in here, the source broadcasts XYZ, A forwards XY, B forwards XZ, and C will mix Y and Z and XOR. And this is equivalent to this case when the source just broadcasts, just unicast XY to A, unicast XZ to B, and unicast Y plus Z to C. So these two scenarios are equivalent, so we just consider the second one, which makes the analysis easier. So so the first thing we have to do to analyze this algorithm is that to answer how many copies of a packet we need to duplicate. So we have this lemma that says at most 2 copies of a packet is necessary to achieve the optimal. So the proof is very easy. Suppose there's an optimal solution that has more than 2 copies of a packet P. So if there are 2 node disjoint paths that this packet travels through, then we can just use those 2 paths and remove all the remaining copies of that packet. Since you have 2 disjoint paths and you have only one adversary that can attack at one node, so this packet is protected, and any corruption by a single node at this packet will be detected by the destination by comparing these 2 copies. Of course, except for the node that duplicates this packet. So in the case that such node disjoint path doesn't exist. So if we look at, so there must be some node in the network that forms a cut, some single node in the network that forms a cut for the paths of this packet. So it can be easy. It's very easy to show that between every 2 consecutive pair of such nodes, there must be either one single path or there exists at least 2 node disjoint paths. Just like this example. Here, A, B, and C is the nodes that form a cut for this packet, and so there's 2 disjoint paths from S to A, 1 single path from A to B, and although you have 3 paths that intersect like this between B and C, we can always find 2 disjoint paths between them, and of course from C to D is the same. So, and then we can come up with a flow formulation of this scheme. So we define WIUV as the number of packets that goes through link UV and which is duplicated by node I. And ZUV is the packet that's been transmitted from U to V and it's not being duplicated so far by any ancestors of U or U itself. So, and then if we take the summation over the incoming links of U, we get this WI in U, which is the incoming packets to U that has been duplicated by I. And the same for outgoing packets, and similar for the incoming packets that hasn't been duplicated before U and after U as a Z in and Z out.
Fine.
Okay. So we can formulate a linear programming to find the capacity to find the max rate that can achieve by this algorithm. So the objective is like this. ZD is the packet that D receives that hasn't been duplicated. And this summation here is the number of packets that D receives in duplication. So you get 2 copies of them, so you divide it by 2. And this C add here is the amount of the capacity of the adversary that it can attack. So we have a bunch of constraints. So the incoming packets to U that's duplicated at I should be 0 if U is not a descendant of I. Because if you're not a descendant of I, how can you get any packet that comes from I? And the flow conservation constraint, if you are not the source of duplication, your incoming duplicated packets must be the same as your outgoing. And this constraint is for the nodes that duplicates a packet. So the packet being duplicated must not have been duplicated before, and then you duplicate only two copies of them. And here, this DI is the minimum number of packets that a node receives that comes in pairs. So this is the pair of packets that you forward both copies. So you can corrupt it safely and cannot be detected by the duplication. And this constraint here is enforced for the broadcast capacity. So this is the amount of packet you forwarded that hasn't been duplicated. The packet you forward that has been duplicated before you, and then the packet you duplicate. But since we consider a broadcast channel, the duplication is free, so you divide it by 2. That must be less than the broadcast capacity. And this term is that the last term is the number of packets a single node can attack. So you can attack the packets that hasn't been duplicated, or the packet has been duplicated, but both copies is routed through you. So we can solve this problem, and of course we can prove that it's an upper bound of the max rate that can be achieved by duplicate and forward. I skipped the proof since the time is limited. So we have a construction to show that this is also a lower bound for the max rate of this duplicate and forward. And so actually we found the best we can do with duplicate and forward is actually the solution of this linear programming. So it gives a lower bound for the security with no adversaries, which can be arbitrarily better than the C minus T given by the linear network coding community. So if we just consider the same example we have before, the solution to the linear program for this topology is that actually it should be R here. Every other ones must be R. So it's just a simple duplication. You duplicate the packets at source, and then it just forwards that. They just broadcast that, and then right. Oh, it's one actually. It's 1 for duplicate and forward. The exact is 1, and since C minus T is 0, it's arbitrarily larger than C minus T. However, is CSEC tight with general nonlinear network codes? It's not. R over C can arbitrarily large because R can be any number greater than 1. But to achieve R, it requires a nonlinear network code. And so the next question is whether this CSEC is tight for linear network codes. And sadly, the answer is no. So we have this. Okay, Rachi come up with this example that in this network, the solution to the linear optimization problem is 11 by 3. But if we can mix it, and if we perform coding in the intermediate nodes, for example here R8, we can actually achieve a rate of 4, which can be proven to be the max rate you can achieve with linear codes in this network.
Can you wrap up in 1 minute?
Okay. I'm finishing in like 2 slides. Okay, so far I basically finished off most of the talk, and this slide is just a very interesting example for linear network codes. So all the links are unicast links, and these links are with capacity 1, and these 2 has capacity of 2. So we consider the transmission of data from S to B, and we can easily find a linear code that can achieve a rate of 2. Just say A, B, A XOR B, and A is duplicated at A, and B just forward B, and C just forward B, and B forwards A plus B, and everything can be checked at the destination. However, if we consider the inverse of this, the backward version of this network, which all the link capacities are the same, just the directions are inversed. So from D to S, actually, if you want to stick with linear network codes, you can never achieve a rate of 2. It's necessary to have a nonlinear code to achieve the rate of 2. However, this nonlinear code is very similar to the linear code being used in the forward topology. So almost all the transmissions are the same, except that A gets 2 copies of A from E and F, C gets 2 copies of B from E and F. So besides forwarding 1 copy of those packets they receive, they will compare the 2 copies of packets they receive and send a 1-bit notification whether they is a match or a mismatch. So you can achieve a rate of 2, arbitrarily close to 2, with nonlinear network codes. So there's something going on with the topology or the connectivity among the nodes in the network that changes the capacity or what you can achieve with linear network codes. So to summarize, for this work we find a lower bound of the secure capacity under no adversary, although it's not very good. And in last year's Alerton, a group from Cornell found 2 upper bounds for the same case, secure capacity under no adversaries. But so far, nothing has been known we haven't found the capacity we haven't found the secure capacity under no adversary either with nonlinear network codes. We haven't even found the max rate we can achieve with linear network codes. So there's a lot to be done along this direction, and that finishes the talk. Thank you.